mute themselves. During the talk, you're welcome to ask questions in the chat, and we'll address those at the end. At the end of the talk, there will also be an opportunity for you to unmute yourselves and ask questions then. So it's my pleasure to introduce Taylor Woehl. So Taylor obtained his PhD in chemical engineering from the University of California, Davis in 2013 under Bill Ristenpart and Nigel Browning. He was an assistant research scientist at Ames Lab from 2013 to 2014 in the Prozorov Lab, followed by an NRC postdoc fellowship from 2014 to 2016 in the Materials Measurement Lab at the National Institute of Standards and Technology. So Taylor and I overlapped there, and that's how I met Taylor, was at NIST. Professor Woehl joined the Department of Chemical and Biomolecular Engineering at the University of Maryland, College Park in 2016 as an assistant professor with an affiliate appointment in the Department of Materials Science, where he leads the Nanoscale Assembly and Electron Microscopy Lab, which focuses on topics including nanochemistry of multi-component nanocrystal formation, fuel-driven dissipative assembly of colloids, colloidal electrokinetics, and protein aggregation. So thank you very much for coming, Taylor. The floor is yours.
Great. Thanks for the nice introduction, Matthias, as well as the invitation. So I'm going to talk to you about a few different projects that we're working on in my lab that we've been working on for about the past 4 years. So it's been a little over 4 years since I started at University of Maryland. And I guess these projects fall under this kind of overarching theme of we like to look at kind of fundamental processes in assembly and crystallization, and this topic of interfacial chemistry has started to emerge over, I would say, the last few years, and not necessarily intentional on my part, but it seems to be important in a lot of the projects that we do. So on the right here, you'll see a nice graphic, which I did not make because I'm not a graphic artist. This is a recent cover art that we had on the chemistry of materials showing nucleation and growth of nanocrystals driven by an electron beam, which I'll talk about today. So I'm very glad to be giving a talk at University of Missouri. I'm actually from Missouri. I grew up in Kansas City, and then I went to undergrad at University of Missouri Rolla. Well, that's what we called it then. I guess they changed the name to Missouri S&T. So I graduated here in 2009 with a degree in ceramic engineering before I went on to my PhD. So it's too bad I couldn't come back in person, but it's still nice to be giving a talk at in my home state. Okay, so let's talk about just a brief introduction in terms of the kind of things that my research group works on and the kinds of problems we're interested in. So as my group name alluded to, we study nanoscale assembly processes, and we study these kind of on a very fundamental level, with the idea that these processes underlie the fabrication and synthesis of advanced materials for things like catalysis and optical materials. So one type of system we work on are inorganic nanoparticles, mostly metal nanoparticles right now. And we study the processes involved in kind of the bottom-up synthesis of these nanocrystals from, say, soluble metal atoms or metal complexes to form these nanoparticles. And so we're kind of on this side of things, not so much on the applications. We also study protein aggregation, so the process of how individual protein molecules become larger collections of proteins called aggregates. These have some significant implications for therapeutics in that they limit the stability of protein-based therapeutics. Finally, we're also interested in colloidal assembly. So here, the building block is no longer, say, an atom or a molecule, but it's a larger nanoparticle made of maybe thousands or millions of atoms. And we are interested in the kind of now colloidal scale processes, right on the size scale of maybe 10 nanometers up to several microns. What types of interparticle interactions are involved in assembly of these nanoparticles and colloids into larger ordered structures, such as lattices, vesicles, these types of things. And so, as I said, we're interested in the fundamental chemical engineering processes involved in these types of advanced materials synthesis and fabrication, not necessarily the application side of things. So to give you a better idea of kind of the broader, I guess our broader outlook on what our lab is doing and how interfacial chemistry fits into all of this, we are very interested these days in how interfacial chemistry processes things like redox chemistry, as well as, say, covalent bonding at interfaces, how those impact, say, the chemical engineering processes like assembly, transport, and crystallization of colloids and nanoparticles. And I just give some cartoons of the different types of projects we're working on right now, a couple of which I'll talk about today. So the first is how colloidal particles behave in electric fields. So here I show a picture of a colloid here in orange and an oscillating electric field, which forms this dipole around the colloidal particle. And what we're finding is that while this is very much a physical process, right, electrostatics governs how this happens, actually the chemistry at the interface between the particle and the liquid is critical for determining the electrostatics, right? So here, right, this is the effect of, say, surface chemistry on this physical process of particle polarization, and then how the particle transports in the electric field, whether it assembles or whether it, say, moves with the electric field, is determined by that surface chemistry. Another type of system we're interested in is heterogeneous nucleation, specifically how chemistry and functional groups at interfaces affect where nanocrystals nucleate, what their morphology is, and what the thermodynamics of nucleation is. Another system we've recently started working on is chemical reaction-driven self-assembly. Here we take a collection of, it could be nanoparticles, colloids, or we're even doing this with proteins that have some type of ligand on the surface, which can be converted over to an activated form by adding some type of chemical fuel, right? This is a fast process, and essentially we activate some of these ligands and it makes the building blocks prone to assembly. And depending on how we do this, we may get irreversible assemblies, which we don't want, or we may get these nice, what are called dissipative assemblies, which then undergo a reverse reaction and go back to the original state. So here again, this process relies on these covalent bonds forming at the interface, as well as forward and backward reactions at the interface now dictate assembly of the nanoparticles, proteins, or colloids. Finally, we are working on protein aggregation as it pertains to stability of biopharmaceuticals. Here we're interested actually in the surface chemistry of protein aggregates and how that affects how these aggregates interact with the immune system. Now, we're not doing much immunology. More, we are coming up with new methods of characterizing, say, the surface chemistry of an individual protein aggregate to determine, for instance, what domain of the protein is being presented on the surface of the aggregate. How can we quantify that? How does the particle size affect that, right? So you can see kind of this common theme among our research of thinking about how interfacial chemistry affects transport processes, assembly, and crystallization. Okay, so I'll talk about two of these today. Let me pull my timer up to make sure I don't go over too much. The first one I'll talk about is visualizing heterogeneous nucleation using a method which we specialize in, which is called liquid phase transmission electron microscopy. After that, I'll talk about some of our works in colloidal electrokinetics. So just a brief overview of kind of the basics of nucleation. I know maybe a lot of chemical engineers don't think about nucleation very often. So nucleation is the very first kind of physical process that happens when you have a phase transition. So let's start here on the left with a supersaturated solution of atoms. This could be any type of atom dissolved, say, we're interested in liquid phases. So let's assume here we have a solution, say, of metal atoms dissolved in a liquid phase that exceeds the solubility of the solution. So we have a supersaturated solution. This creates a thermodynamic driving force to condense the solid phase, these atoms into a solid phase, and we form a solid nucleus. And then atoms will add to this nucleus to grow into a larger crystal. So this process is very important for things like nanoparticle synthesis. It's important for synthesis of pharmaceutical small molecule drugs. And right, there's a thermodynamic driving force for nucleation to happen. However, there's a kinetic barrier for this to occur as well. And that's because we need to create new solid-liquid interface. And this gives us an unfavorable increase in the Gibbs free energy of the system, while forming just a new bulk solid is thermodynamically favorable. If we sum these two together, the surface and the volume term, we see, and we plot the delta G as a function of particle size, basically, right? We see there's an energy barrier to nucleation due to this surface term. And basically, then it says we need to reach a certain supersaturation in our solution to actually overcome this energy barrier. And the size of this energy barrier actually is dependent on what the specific nucleation mechanism is. And so for homogeneous nucleation, where we form crystals in solution, it's very high. However, if we're going to form crystals at a solid liquid interface, the barrier becomes reduced. So the question we're really thinking about here is, so we can think about heterogeneous nucleation in kind of macroscopic sense. We know crystals like to form at interfaces. It's easier for them to form at defects. So, but I show this nice GIF of a glass of beer, and you see the bubbles coming off the bottom. Okay, so we know these are defects, but the question we're really focused on here is, what are the specific defects at which the nucleation occurs, right? Is it the functional groups? Is it surface roughness? Are there surfactant molecules that are causing nucleation? And how can we look at this system with high enough spatial resolution to know what that actual defect is, which is leading to nucleation? And the problem is that most conventional experimental approaches do not allow us to probe nucleation both at a nanometer size scale, so on the size scale of these defects, as well as time scales that are short enough and long enough to see nucleation. And nucleation really spans a large range of time scales from about nanoseconds up to minutes. And so we need a method which can at least get kind of the seconds to minutes time scales and also get this nanometer size scales. And so a nice solution for this is electron microscopy. And so the technique we specialize in my lab is called liquid phase transmission electron microscopy. So we use a standard transmission electron microscope. This is a instrument at UC Davis. I have a picture of here. And then we use a specialized microfluidic sample holder. So the sample holder contains 2 silicon chips. Each chip has a thin electron transparent coating of silicon nitride on it. And then each chip has a hole etched out in the center of the chip, which is basically our viewing window. And so we place a droplet of liquid between these 2 chips. We sandwich it together to form a very thin liquid layer, which is transparent to the electron beam. And then we seal this whole thing together. And then this is hermetically sealed from the high vacuum of the electron microscope. And so a cartoon of this would shown here on the right, where we have kind of 2 chips. We have a hole in the middle. Right here is a very thin membrane spanning this hole. And then this contains the liquid layer. And then we can put whatever we want in here. People have put nanoparticles. People have put proteins in here. People have put live cells in here. You can put all kinds of nanometer scale objects inside of here, as long as they're small enough, less than a couple of microns. And so what we could do with this is then basically form movies of different processes happening in liquid. We can do this in real time with real-time kind of video rate imaging. So on the left, I show silver nanocrystals forming over time. So these black spots are silver nuclei, which then grow into larger nanocrystals. This is sped up 6 times. And then on the right, these white dots are gold nanoparticles, which we can see are diffusing around and assembling into straight and branched chains. And so this lets us take movies of these processes at resolutions which are much higher than you could get with optical microscopy. Okay, so one topic we focus on a lot in my lab is thinking about how the electron beam interacts with the water in the liquid cell. And what happens is when we are essentially hitting our water with 200 kiloelectron volt electrons, very energetic, much higher energy than the bond energies of the water. What we do is we radialize the water. This breaks the oxygen-hydrogen bonds, and it forms a number of highly reactive species. And you can see this process is very complicated here on the right. I'm not going to go over all of it. I put this here basically to show that we get We get a number of species forming in solution, ranging from molecular species like hydrogen, hydrogen peroxide, to things like ions, as well as radicals like hydrogen radicals and aqueous electrons. So it turns out, which is very nice for metal nanoparticle systems, that these two species, hydrogen radicals and aqueous electrons, will reduce soluble metal precursors, say like silver plus, into atoms, which then will nucleate and grow into nanocrystals. So we can basically image nanocrystal nucleation and growth, and at the same, we can stimulate it with the electron beam and also use the electron beam to directly image it while it's happening. I'm trying to get this out of the way. And we form a number of species because back in the 50s and 60s, people were very interested in kind of building nuclear reactors. They had to really understand how ionizing radiation interacted with water. So we have a ton of knowledge actually from the 20th century on what are the concentrations of these species. We have models for modeling how much of these species are formed. And we can take all these models developed for nuclear reactors and we can apply them to our experiment in our kind of microfluidic reactor. So I'll try and keep this a bit short because it's not too important, but just to show you that the main two reactions, say if we have a metal ion in solution, right, are reduction by aqueous electrons and hydrogen radicals. We have a very important parameter, which you'll hear me talk about, which is called the dose rate. And this is essentially the amount of energy absorbed by the sample per unit time. And the dose rate is proportional to the flux of electrons we're putting in, which is proportional to the magnification squared of our image. So at a low dose rate, we have a relatively low concentration of these reducing species. High dose rate, we have a high concentration. And we form a steady state very quickly because this volume right here is actually about femtoliters in volume. So if you do the diffusion modeling, you find that steady state is reached in milliseconds. And so basically dose rate is our knob for controlling how much reducing species we have in solution and for how fast these two reactions proceed, right? And we can model this with models developed, again, back in the 50s and 60s for nuclear reactors to determine the steady state concentrations of the important species for what we're studying. We can estimate the supersaturation ratio, which is an important parameter for nucleation. Right, we do some reaction diffusion modeling. Right, we know that we have silver being converted to silver atoms, silver plus to silver atoms. These can diffuse out of the volume, reaction volume. We can also have more silver plus diffuse into the reaction volume. So it's kind of this continuous process, and we set up a steady state concentration profile within this volume. We can model this with the reaction diffusion equations and determine, within our image area, which would span kind of this whole M shape for each of the image magnifications, we can determine the concentration of silver atoms. And knowing the approximate solubility of silver atoms in solution, we can determine the supersaturation ratio. And we see it increases as we increase the magnification. So this gives us a nice knob to tune now our nucleation parameter supersaturation ratio, and we can approximately know what it is. Also, we see that the precursor concentration determines supersaturation ratio as well. And I'll note these numbers are huge, right? 1,000 up to 100,000. This is pretty typical actually for a typical nanocrystal synthesis that you would do on a wet chemical lab. So let's see what the effect of magnification really is on silver nucleation kinetics. So if we look at a few videos of this actually happening, at a relatively low magnification, we see kind of sporadic nucleation at the beginning. And then after about 20 or 30 seconds, we form a lot of nuclei across the image area. And then these nuclei grow into larger silver nanocrystals. At the end, the nanoparticles become about 20 to 30 nanometers in size. But at much higher magnification, I think here we double the magnification. We see within 5 seconds, we've basically covered the entire image area in nuclei. And then after that, it's just growth of nanocrystals. So we can do some image analysis on this process and basically count, what is the number of particles as a function of time, which would allow us to calculate the nucleation rate of these silver nanocrystals. right? So we are here showing now the nucleation rate, nucleation number of nuclei per nanometer squared as a function of time, right? We see as we increase the image magnification from 80,000 times up to 150,000 times magnification, right? The slope of this initial linear portion of the line, which we are calling the nucleation rate, increases. And we can do some fitting actually to classical nucleation theory, which in general is not a great theory, but it is pretty good for heterogeneous nucleation, which is what we're looking at. And we see, I'm not going to go through all the details of this again, but we see that R is the nucleation rate, right? And it should have a linear dependence on 1 over the natural log of supersaturation ratio squared, right? Where the y-intercept is natural log A, which is an exponential prefactor. And so some parameters in here which are important and which our fit reveals to us really is the interfacial energy, which is the interfacial energy between our nuclei and the solid-liquid interface. And when we fit these data, we find an interfacial energy of about 145 millinewtons per meter. There really is no literature value to compare this to, but we know that this is a reasonable value. Typically for nucleation at solid-liquid interfaces, you get something between about 50 and 200 millinewtons per meter. And also importantly, we see that we get an approximate kind of negative linear correlation between natural log R and this 1 over natural log's supersaturation ratio squared. Of course, we only get 3 data points, but these data took a long time to collect. So this gives us some confidence that what we are seeing is heterogeneous nucleation. Our next question we wanted to ask was, well, what about spatial variations of nucleation kinetics, right? We could, perhaps do this type of experiment where we're looking at nucleation as kind of a macroscopic process, right? We could do this perhaps with, say, X-ray scattering or maybe even optical microscopy. What liquid phase TM really gives us is this really high spatial resolution that's going to let us see, okay, as a function of position along our solid-liquid interface, how do the nucleation kinetics vary, right? So let's now go from looking at nucleation like a macroscopic process to looking at it as a very microscopic process and looking at kinetics of kind of individual nucleation sites. And so how do we do this? So what we've done is to generate these things called nucleation induction time maps. And so I'll explain here what that means. So basically, sorry, go ahead. Did somebody have a question?
No, go ahead.
Okay, sorry. Okay, so we have a video just of nanocrystal nucleation happening here on the left. What we do is we worked with our collaborator, Chi-Woo Park, who's an expert in machine vision at Florida State University. And what he was able to do was essentially track the X and Y coordinates of each nuclei, so where each particle forms, as well as the time at which they form in reference to time equals 0. And those are the nucleation induction times. It's basically the amount of time it took for us to visualize or see that nuclei form, right? So a short induction time would mean kind of fast nucleation kinetics. A long induction time would mean slow nucleation kinetics. Then we plotted those XY coordinates and interpolated the induction times into a 3D surface, right? So each of these black spots here on the right is the nuclei position extracted from the movie on the left. And then the color is a 3D surface we fit to all the known induction times for each black point. And so here we've kind of modeled or fit what the nucleation induction time is across the entire interface. And we see that it's very splotchy. And this was very surprising to us that we would have, regions where nucleation is very fast and regions where it's very slow, like these red regions. And so that's in this study, what we did was to try and understand why this was happening. And so we did this as a function of a number of variables. So we varied the supersaturation ratio, both by changing the image magnification, which we know increasing mag increases the supersaturation ratio, so follow the arrow to the right, and also increasing the precursor concentration from 0.1 millimolar to 0.2 millimolar. So again, the red and orange areas are regions of locally slow nucleation kinetics. and the blue-green areas show regions of locally fast nucleation kinetics. So let's look at the top row first, going from kind of a low supersaturation here on the left to a high supersaturation here on the right. At low supersaturation ratio here on the left, so I will say we don't know the exact supersaturation ratio for this condition, but let's talk in relative terms, I guess. So we see most of the interface, most of the image region, right, is dark red with a few kind of blue splotches. So most of the nucleation kinetics were slow, except for a few sites that had very fast nucleation. You can see this very localized down here. As we increase the supersaturation ratio, we get kind of the splotchiness inverts, and we get these big domains of green forming and get kind of smaller domains of red, right? So this would be fast nucleation. This is kind of slow nucleation here. And then as we go to the highest magnification, most of the region is now blue, and then a few splotches of domains of red, which would be kind of slow nucleation domains. We see something similar qualitatively happening for a higher precursor concentration. However, everything is kind of shifted to faster nucleation rates, right? Because we know that our supersaturation ratio is higher. Once we get to this highest ratio down here, 0.2 millimolar, 150 kx, pretty much the entire area is blue. We kind of have almost a uniform nucleation kinetics across the interface. So what is the mechanism for this happening? Why do we get these domains of kind of rapid nucleation, domains of kind of sluggish nucleation kinetics? So let's look at what some possible nucleation mechanisms could be. So this is a plot out of a recent article from Jim Diorio's group at PNNL, where they show kind of the three typical nucleation mechanisms that people see in liquid phase nucleation of crystals. So the first is classical nucleation theory, which I've already talked about, right? We have a single energy barrier to forming a nuclei, and we have to get over that before the phase transition can happen. There's also this more recently discovered nucleation mechanism involving pre-nucleation clusters, where we can have multiple energy barriers, and we form these kind of metastable species prior to forming the final crystalline phase, which would be down here. And then at very high supersaturation ratios, you can have spinodal decomposition, where you essentially just get a rapid phase separation of the two species in solution, which is dictated solely by diffusion. So actually, initially, we thought spinodal decomposition looked pretty good for us because these domains that we see in our maps look a lot like this cartoon here. However, we did some calculations in terms of the diffusion times, and find that our domain sizes are much too large for the diffusion timescales expected in our system. Really, you should get domain sizes on the order of about 10 nanometers, which was shown by Ukir Mirzadov's group at NUS a few years ago. And this is a liquid cell TEM study too, but they found gold-rich domains on the order of 10 nanometers, right? So much smaller than our system. And so spinodal decomposition doesn't make sense for us. So the other one, which I don't really show explicitly here, is heterogeneous nucleation. And this is the idea that we may have defects at our interfaces which lead to, say, preferential nucleation in some spots. And so we kind of ran with this idea and went on to kind of explore the nature of what these heterogeneous nucleation sites could be. And the first question we asked was, well, is it surface roughness? Do we just have some regions which have roughness, which are more prone to forming nuclei than others? So we did atomic force microscopy measurements at our solid liquid interfaces, which I guess I haven't mentioned what they are. They're CVD deposited amorphous silicon nitride. And so when we did the AFM, we found that this CVD silicon nitride is actually very thin with almost no surface roughness, about 2 nanometers maximum surface roughness, right? So we kind of ruled out surface roughness here because these interfaces are close to atomically flat. The next question we asked, well, could it be the surface chemistry of the silicon nitride interface? We know that the way that silicon nitride is deposited, that the silicon nitride ends up having both silanol, SiOH, as well as silamine groups at the interface, right? Some of these can be charged due to deprotonation or protonation, right? And so we asked the question, is the surface chemistry non-uniform on a similar spatial scale as the nucleation kinetics. And so for this, we did chemical force microscopy. And here we essentially operated our AFM in what's called attractive mode, which is the AFM probe doesn't really probe the topology of your surface anymore, more that it's probing kind of the colloidal interactions of the probe with the interface. And to do this, we made our silicon nitride AFM tip hydrophilic, as well as we made our interface hydrophilic. And so what we see if we look at the CFM map, which is here on the right, this is a phase map of our interface. And what people have found in the past is that these dark regions where the phase is lower, these correspond to regions that are more hydrophilic than others, where we get an attractive interaction between the tip and the interface, right? And so what we conclude here is we do see some kind of chemical patchiness on the surface, and we see that some regions are much more hydrophilic and some regions are much more hydrophobic, like these bright white regions. To further support this idea, we did covalent labeling of the functional groups on the surface using gold nanoparticles. And so we used some conjugation chemistry methods that you would use, say, to conjugate biomolecules together, but instead we conjugated gold nanoparticles specifically to silanol and silamine groups on the surface. So it's not that we didn't dry the nanoparticles on the surface, we used chemical covalent coupling. So wherever you see nanoparticles, this is where the functional groups are. And again, we see a very kind of patchy surface in terms of where the nanoparticles like to bind and where the surface functional groups are. And so from this, we can conclude that the surface functional groups segregate into domains of on the order of 50 to 100 nanometers, which is similar to the size scale of what we see in our nucleation induction maps. And so we conclude really it is this non-uniform interfacial chemistry which is causing this nucleation phenomenon we observe. So with that, I'll conclude. We've been able to use liquid phase TM to probe nucleation kinetics kind of at a single nucleation site scale. And we are continuing to work on this system to map out kind of more complex interfaces now, say like polycrystalline interfaces and how metal nanocrystals form on them for applications like solar cells and the catalytic materials. Okay, so in the interest of time, I'll move on to my next topic, so I have some time to talk about it. Okay, so I'm going to switch gears a lot on you now, and I want to emphasize now we are moving to a micron scale system. So the movies and the videos and images I'll show you are from an optical microscope, not from an electron microscope. So we're going up in size scale by about an order, no, 3 orders of magnitude. So in this project, we're looking at how electric fields affect the assembly and transport of colloidal particles. And so this process has been studied for quite a while. Again, back in the early 20th century, people were using things like constant electric fields to deposit thin films of nanoparticles. More recently, back in the 90s, people were investigating oscillatory electric fields, so AC electric fields, for assembling colloidal particles into nice ordered structures, which could be used, for instance, as photonic materials. So this video here shows assembly of, I believe, 2 micron polystyrene particles into colloidal crystals. And so the electric field we use here is about 500 hertz, so it's a relatively low frequency. And what happens is that when we apply this electric field, each colloidal particle is polarized, and we form contractile fluid flows directed towards each particle, which then causes all the particles to clump together and form these 2-dimensional aggregates. In terms of the more complicated mechanism, this phenomenon is known as electrohydrodynamic flow, or EHD flow for short. So this cartoon shows what's really happening here. And it is that the electric field, which is normal to the electrode surface, polarizes the colloidal particle. For our system, the dipole of the colloidal particle is pointed in the opposite direction, right? And this creates a tangential electric field that is directed along the electrode surface towards the colloidal particle, or away, depending on what phase of the electric field you're in. And then this drives a body force on the induced charge here at the electrode, which then drives a bulk fluid flow, which for most cases is directed towards the particle, right? So we get streamlines like shown here in the simulation on the top right, right? So where the colloidal particle is here in white, and the streamlines are directed towards the particle along the electrode interface, and then up out into solution. This is what's known as a second order electrokinetic fluid flow, meaning that it goes as the velocity of this fluid flow goes as the electric field squared, which explains why it would happen in an oscillatory system. And it also goes as basically the polarizability of colloidal particles. So how strong that dipole is also determines how fast the fluid flow is. So what we found during my PhD and what other people are beginning to find is that the fluid flow behavior as well as the assembly behavior of the colloids is very much pH dependent. If we put particles at pH 6.5 electrolyte, they assemble. If we put them in sodium hydroxide at a pH of 10, they don't do anything, or they actually separate from each other. We found that putting particles at high pH can cause them to levitate very far from the electrode. Particles can levitate on the order of 20 microns or more off the electrode surface when we put them in sodium hydroxide, and they don't do anything when you put them in KCl. Ning Wu's group at Colorado School of Mines has found this can affect the propulsion of these asymmetric colloidal dimers. And recent models are finding that really it is, like I said, the interfacial chemistry on the colloid surface, things like the particle's zeta potential or its surface charge, which determine kind of how fast the particles might aggregate. So this is the aggregation rate constant, or how fast that EHD fluid flow goes. So these are some recent simulations from Colorado School of Mines, right, showing that you can actually get a reversal in the direction of the fluid flow if you really increase the surface conductivity or the surface charge of the particle. So we've been working on actually kind of actively generated electrochemical generation of pH gradients. And this was really interesting to us given how much pH affects EHD flow and EHD assembly. So we've been using these molecules called electroactive molecules. The kind of most vanilla one you can think of is benzoquinone. So that's what we've been working with. And it's just a very simple small molecule, right? It has these two alcohol groups on it attached to a benzene ring. This makes it quite easy to remove the proton or add the proton using an electrochemical potential. This happens within the electrochemical window of water. And so we can basically dissolve some benzoquinone in water. We can apply a DC potential to it, and we can generate a pretty significant pH gradient at the electrolyte interface. And we've shown this happens with a platinum microelectrode and a pH-dependent fluorescent dye. And we can see, either increase or decrease in the fluorescence, whether we, apply a positive or a negative current. And this corresponds to, right, either pumping protons into solution or consuming protons at the electrode surface. So our colloidal system kind of looks like this now. We have two parallel plate electrodes. In between these, we've put a dilute suspension of colloidal particles. They are heavy enough and large enough that they sediment to the bottom electrode by gravity, but they remain stable. They don't stick. And then we apply both an AC electric field, right? This drives the EHD fluid flow, and a DC electric field, which drives the benzoquinone redox reactions. And in this orientation where the cathode's at the bottom, right, we get an alkaline pH down here, and we can get acidic pH up at the top. And so our question we asked was, how do these microscale pH gradients affect EHD fluid flow and colloidal assembly, knowing that things like zeta potential and solution pH are very important in determining how EHD fluid flows come about. So we see that the redox potentials for benzoquinone are around 0.5 volts and negative 0.3 volts for our specific electrode system. So here Q is benzoquinone and QH2 is hydroquinone. So this is the protonated version. We can model the pH gradient using reaction diffusion equations. And for a reasonable current density, we find we can get upwards of a pH of around 9 at our electrode-electrolyte interface. And this decays to neutral pH over about 50 to 100 microns. Right, so this just gives you an idea of the extent of the pH gradient. And so we did a number of kind of systematic and qualitative experiments just looking at how do different conditions affect how the particles behave. We found that if we don't have any benzoquinone in solution, that the colloids are pretty much unaffected by a DC electric field. And so what we did here was to take some polystyrene colloids. Again, they're sitting near the bottom electrode. We apply an AC potential to drive this EHD fluid flow. This causes them to assemble. And then we apply an increasingly negative DC potential. And we can see that the colloids remain assembled into colloidal crystals. Nothing happens. However, when we now add some benzoquinone to solution and do basically the exact same experiment, here, like I said, we expect to have our pH to be more alkaline near the bottom electrode. So as we increase the DC potential, we're making it more alkaline down here. And you can see that our colloidal crystals, as we increase this DC potential from 0 to negative 350 millivolts, they start to kind of expand from each other as they're being, it looks like they're being repelled from each other, and eventually they explode. Okay. However, if we flip this system around and now we make the anode the bottom electrode, right, this is now going to be an acidic pH, nothing happens, right? The particles remain assembled if we just apply increasingly large positive voltages. And I'll note that we don't ever go above or outside of the electrochemical window of water, because we know outside there we will also change the pH due to electrolysis reactions, right? So we're staying away from electrolysis, and in the hopes that the only electrochemistry going on is that of benzoquinone. We see something similar with polystyrene compared to silica. Applying our negative DC potential in increasingly negative increments, we see our particles eventually disassemble. But instead of kind of remaining in focus, actually the polystyrene moves completely out of focus and moves from the bottom electrode all the way up to the top electrode. And then finally, if we flip our cell over and we make the top electrode the cathode, we see basically the same thing as if the bottom electrode was the cathode and we had our particles down here. For some reason, we can get the particles to stay suspended against gravity if we have our AC electric field on. I'm not sure why yet. But we see that as we increase now, add increasingly positive potentials, right, our particles disassemble and fall apart. So let me summarize now our kind of observations. Right, we found that our colloidal assemblies formed by EHD flows are unaffected by DC bias up to 1 volt, so within our electrochemical window of water, without benzoquinone, and they're also unaffected if we have them at the anode with benzoquinone. Silica and polystyrene assemblies both explode at the cathode in the presence of benzoquinone, and the polystyrene moves from the cathode all the way up to the anode and actually reforms post-back assemblies. And then polystyrene assemblies at the cathode explode and move to the bottom electrode. So what's going on here? For one, this is a very complicated system, and so we've been coming up kind of with a toy model. It's not perfect yet because there's a lot of stuff going on. So the interesting part of this system to me is that we don't have particles with static surface chemistry, right? As the particle moves through the pH gradient, its surface charge changes, right? So when the particle is, right, our particles have carboxylic acid groups on their surface. So at very low pH or at very low high pHs or very near the electrode-electrolyte interface, our particles are highly charged. As they move up in the pH gradient, I guess down the pH gradient, their charge reduces, right? Because we are starting to protonate some of these carboxyl groups. We did some control experiments and we find that, right, the zeta potential, which is our surface charge, right, can be upwards of -80 or -90 at the electrolyte interface, which is pretty high. And then as we move it into solution, it can be almost cut in half down to about 40 to 50. However, the opposite happens for the strength of the dipole on the particle. And that's because this dipole strength is inversely proportional to zeta potential. So when we're very close to the electrode, our particle polarization is relatively small because our surface is very conductive on our particle. As you move into solution, the particle becomes more polarized. And so what our hypothesis is here is that the behavior we see in terms of this levitation, as well as the exploding of the assemblies, is controlled by kind of competing first order electrokinetics. So this would be just motion of the particle in the electric field by electrophoresis, and second order electrokinetics. And these are our electrohydrodynamic fluid flows and our dipolar interactions. So we have a number of competing electrokinetic forces. I think in the interest of time, I'll go quickly over this. In the vertical direction, really we're balancing gravity, which is pulling the particles down, and then we have electrophoresis pushing the particles away from the electrode. And it turns out that if we do the calculation in terms of our interaction potential between the particle and the electrode, we find that with benzoquinone, with our pH gradient, we have this nice potential energy minimum around 8 microns, which is about where the silica particles sit when we apply an electric field with benzoquinone. However, if we don't include a pH gradient in our system and we assume just a constant surface charge, right, we predict that the silica particles are just going to remain right next to the electrode surface, which is what we see in our experiment. So basically, we have a balance between electrophoretic forces and gravity, which forms this potential energy minimum, about 7 to 8 microns from the surface. For polystyrene particles, our model predicts that the particles will move from the bottom electrode to the top electrode because they have a density which is much lower than silica. And we could see kind of in this picture, right here, we have an imbalanced force, right? The electrophoretic force always wins out over gravity. For silica, right, the forces are approximately balanced. Okay, let me skip that. And so for the assemblies exploding, I'm going to skip a few slides actually. I'll just show this kind of qualitative picture. Right, for our silica assemblies exploding, right, when we have no DC potential applied, right, we just have these attractive forces due to EHD flow, which are dominating and they're bringing our particles together. However, as we start to apply our negative DC potential, we start to make the pH more alkaline here, right? We're starting to get now electroosmotic flows in the opposite direction, which are pushing our particles apart, and our EHD flow is getting weaker because our particles becoming less polarized. Eventually, we get to a point where the electroosmotic flow overcomes the EHD flow, right? This has become almost reduced to 0 because we are our particle is becoming less and less polarized as the pH goes up. And when that balance shifts from attractive to repulsive, the assemblies explode. And that's the kind of behavior we would expect here. Okay, I'll skip this and I'm pretty much out of time. So I'll conclude here and say that you know, the interesting part of these systems is that these pH gradients create dynamic colloidal surface charge and polarizability, which we don't see in normal electrokinetic systems. We expect we can use these to separate different types of colloids. I'll just show you this video really quick, based on their density or their surface properties. So here we have a mixture of silica and polystyrene, and we can almost exactly separate this mixture of particles using this method. So one of them can be pushed to the top electrode and one will go to the bottom electrode. Okay, and with that, I will thank all the students who worked on this. So Mei Wong and Umesha Disnyaki are both PhD students who worked on the nucleation. Jackie Weaver was the main student working on the colloidal electrokinetics, and more recently, Meta Rath is working on that. And I'd like to thank our funding, especially ACS PRF and NSF, for supporting the two projects I talked about today. And with that, I'll take any questions.
Awesome, thank you, Taylor. So we have one question in the chat. The question is, on slide 14, were there any initiating events that caused the shift from negligible nucleation rates to the constant region? Also, how quickly did the nucleation complete? That is, how long did it nucleate at the constant rate? And then third part of the question, finally, did the kinetics of the nucleation allow overshoot of the equilibrium nucleation? Is that clear?
Let's go back to slide 14 and look. There we go.
Right, so the question was, were there any initiating events that caused the shift from negligible nucleation rates to the constant region?
I see. So you're talking about probably the red and blue plots where we have initially, no nucleation, and then at some point it happens. So this is well known to happen in the nucleation literature because nucleation is a stochastic process, right? It requires kind of thermal fluctuations to eventually form a nuclei of the critical size, right? This is the amount of time it took that to happen. And on top of that, this is the amount of time for the nuclei to grow large enough for us to see them. So we have our spatial resolution here is 1 or 2 nanometers. We predict that the size of the nuclei is actually about half a nanometer. So the nuclei has to grow a little bit into a nanocrystal before we can even see it. And so, right, this lag time is the compounding of those two effects of the stochasticity of nucleation as well as the time it takes to grow to a detectable size. How long did it take nucleation to complete? Well, we can see, you can actually see it in the red plot, right? It goes flat right here. So about 80 seconds is when we stop seeing new particles. And that happens because, for 2 reasons. We fill up all the nucleation sites, basically. And then it becomes more favorable instead for silver atoms to just add to existing nanocrystals instead of nucleating. So the path of least resistance changes, right? At the beginning, the only option the metal atoms really have is to nucleate at the interface. And then once the supersaturation ratio gets small enough and we fill up enough nucleation sites, then it's easier for a metal atom to just attach to an existing nanocrystal. So it completes right here. And we can see for the green one, it completes up here. You can see the slope changes, which we're not sure why that happens yet.
Okay.
And then,
yeah, did the
I don't understand the final part of the question.
Yeah. Overshoot of the equilibrium nucleation. I guess, Luke, if you can clarify your question. And if anyone else has other questions, please feel free to put them in the chat, or you're welcome to unmute yourself and ask.
I guess I'll ask one. So I think you said this, and I just didn't quite follow you all the way to the finish line. But when you have the TEM on, when you're scanning this through the surface, it seems like the electrons would change the rate or the charge density or something, change your nucleation rate as a fact that you have either light shining through them or electrons on it. Do you know if that's happening, or is that just a minor effect that can be ignored?
That's a good point. Actually, it's something people are talking about in this field. We only consider the chemistry going on that's induced by the electron beam, right? That is the formation of radicals in solution. We assume we assume that's the dominant effect. There are people talking about the electron beam generating electric fields in our sample, which it can do. And the electric field will change the thermodynamics of the nucleation. You can add an extra term to that classical nucleation theory, or the electric field. The issue is the modeling is not accurate enough yet for us to know whether that's a significant effect. And also we have this interface, which is silicon nitride. We're also knocking electrons out of the silicon nitride due to secondary electron emission. And creating vacancies inside the silicon nitride. That could possibly lead to, say, electron transfer to the interface, and that could also induce some nucleation as well. So kind of think of that almost as an electrochemical process. Again, we can't model that, and the models just aren't good enough. I mean, this is kind of the best we can do in terms of doing a quantitative study.
Yeah, but if you were to do that, wouldn't you try changing like the current, the emission current, and seeing if that would have an effect?
Yeah, and we do. That's what we do in these
Okay.
experiments is we also do things where we change not just the magnification, but the emission current.
Right, you would change the emission current, the magnification. I mean, that's just the focus of the spot, right? I mean, that's just spot size.
Well,
but you can also change spot size.
Exactly. So we do change the spot size, and actually the reason I don't show that data here is spot size doesn't affect nucleation rate.
Yeah, I wouldn't expect it to.
It only affects the growth kinetics. So if you increase the spot size or the beam current, your growth rate's going to go up.
Right.
But your nucleation rate doesn't go up. They're separated from each other.
I agree. I agree. Yeah. And I don't think the beam voltage is going to have, I mean, you're at such a high beam voltage those things are just screaming by.
Yeah. We haven't, right? We've changed the beam voltage in the past, and it doesn't have a huge effect because the cross sections don't change. Your inelastic scattering cross sections don't change so much at this energy.
Correct.
Yeah.
I think that goes back to your answer to the effects of the answer, Carl. I think you've got your answer.
Yeah.
Thanks.
No problem.
Great. Luke did ask provide some clarifying information. I don't know if you want to read that and if you have more insights.
Yes. So yeah, you're right. I kind of see what you're saying now. So we go from this constant nucleation regime back to a flat. And that's because we've decreased the supersaturation of the solution enough now that there is no driving force for nucleation anymore. Instead, we just have crystal growth is occurring because that's a very low activation energy process. Yeah.
Okay, cool. If anyone else has questions, please chime in. I had a couple. So I thought it was really interesting and compelling how you were trying to track down and figure out whether it was the surface distribution and surface functional groups on the silicon nitride that was causing this nucleation behavior that you were observing. You had some pretty compelling evidence, some cool results. I guess, can you talk a little bit about efforts to try to correlate them one-to-one? Like if you could image the functional groups on a specific silicon nitride window and then do nucleation of nanoparticles so you know where the functional groups were during the nucleation? Do you have thoughts in that direction? What are the challenges? Why can't you?
That was, I guess, our initial aspiration, but I think we quickly dispelled with it for a few reasons. I mean, you could see the size scale of the AFM images is quite a bit smaller than what it was for the TEM images first. And I guess in our minds, well, just kind of practically speaking, the idea of we put water on our sample, we do AFM, and then we have to transport our sample between buildings, put it into the liquid cell holder and then into the TEM. I guess the idea of finding that same region again was really daunting to us.
Yeah. And
it was more of a practical, I think in principle, you could do that correlative experiment. And I think it was also more like, do we have enough money to spend another year on this? But in the end, I guess we thought the data was compelling enough that we could go ahead and not have a one-to-one correlation. But I'll say it's possible. What's not possible, I think, is doing the experiment afterwards, right? Once we've put the nanocrystals on the surface, there's really no way to go back and say, okay, what functional group is that nanocrystal on? There's no way to remove the nanocrystals from the surface after we finish the experiment.
Right.
So it was more like, transporting a sample between two in situ measurements, correlating spatial position down to a 1 nanometer resolution is a really big practical challenge.
Yeah. All right, cool. Thank you, Taylor. Our time is up. I'm going to talk to you after this, but let's go ahead and wrap up this presentation part, and then we'll switch you over to the one-on-one.
Okay, I should join the other room.
Yep, let me stop the recording.